Alright, we've got section 6.3b, more integration by parts. Okay, and we're going to start off today with an example involving area under the curve. So I want to find the area under the curve I want to find the area of the region enclosed by y equals to ln of x equals to e, and the x-axis. Okay, so I'm not going to give you a picture for this either, so you really need to stop and think, what region are they talking about? I hope you guys know what the graph of ln of x looks like. Looks something like this. Has an x-intercept of 1, and I want this curve, I want the line x equals to e, which is a vertical line that crosses at e, and the x-axis right here. So the region that I'm referring to is this little space in here. Well, how do I represent that area? It's going to be the integral from 1 to e. Remember, if we think of this as a Riemann sum, all of the rectangular approximations all the way from 1 to e, so that goes horizontally. And under the curve, so between the curve and the x-axis, so that's going to be ln of x dx. Okay, so from yesterday, do you guys remember how to integrate ln of x dx? It's going to be x ln of x minus x from 1 to e. And again, if you don't remember that, that's going to be the regular integration by parts that we had done previously. And you need to be able to simplify this. ln of e is equal to 1, ln of 1 is equal to 0. So this is going to give us e minus e, which is 0, and then we have 0 minus 1 to give us 1. So the area under the curve is a nice number, 1. Alright, let's try another one. Let's try to integrate x cubed e to the x dx. Okay, now from your homework yesterday, did you guys have trouble with number 15? Were you guys able to figure that one out? That particular one, you had to do integration by parts 2 times, right? Well, on this one, we're going to have to do it a couple times as well. And here's a little tip for you. Whenever you have a polynomial part of your function here, you want that to be your u, because the e to the x, which is going to be your dv part, you have to integrate it, and that one kind of just repeats. It doesn't ever really go away. So we want that to be the dv part. So I'm going to let u equal to x cubed, and dv will be equal to e to the x dx. And I'm going to call this, I'm actually going to call this u1 and dv1. Then I'll have du1 equals to 3x squared dx, and my v1 is going to be e to the x. So that part's nice and simple. So using my integration by parts, I'm going to have uv, so x cubed e to the x minus v du. So now I have 3x squared e to the x dx. Now I know you guys are looking at that and thinking, oh, I still can't integrate that. But this has gotten better, because if you notice, this started out with x cubed. Now we only have an x squared. So the power has reduced by 1, and we're closer to our goal of being able to integrate. Now, I'm going to do this next part here with a strategy that I recommend you guys do. Because of the sign change problem, which many of you will forget, I'm going to change this to plus a negative. I'm going to keep this as a negative 3x squared. So this first part over here, I'm done integrating x cubed e to the x plus. But this second part, I don't know how to integrate that, so I'm going to use integration by parts again but I'm going to let my u1 equal to negative 3x squared. And I'm going to let the u2, and dv2 is going to be e to the x dx. So I'll get negative 6dx here, and I'm going to still get an e to the x over here on the right. So when I write this second part out with my integration by parts, I can just add uv, which happens to be a negative 3x squared e to the x minus v du. And notice this is already a negative, so it's going to turn into a positive 6x e to the x dx. I don't need to worry about the distributing of the negative sign if I go ahead and write my negative right in here already with my u sub 2. Now I know you guys are looking at this and thinking, wait a minute, we need to integrate by parts one more time. So yes, we do have to do it 3 times. So sometimes you have to do this repeatedly. And actually I could have told you ahead of time that I was going to have to do it 3 times because it's an x cubed, the third power. We would have to take the derivative 3 times in order to get it down to a constant. So using my integration by parts one more time over here on the right hand side, let's let u sub 3 equal to 6x and our dv sub 3 equal to e to the x dx. So I get 6dx and I get another e to the x. So those dv's are hopefully really kind of nice to use. So this last part here, plus uv, so that's going to be 6x e to the x minus v du, 6 e to the x dx. And if you look now, this very last part, our integral, we can actually integrate that. We don't need to do integration by parts anymore. So I've got x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. I am done integrating. I had to do it 3 times, and now that I'm done, I put in my plus c at the very end. If you would like to factor out the e to the x term, because all 3 of these, or all 4 of these terms has an e to the x, you're free to do that, but by no means is it necessary for you to do. Okay? Now some of you guys are looking at this and thinking, holy moly, that is a lot of integration by parts, and I'm going to get it all mixed up. There is another method, and I don't want to say method. There is another way to write out our integration by parts, and it's something called tabular integration. Now, tabular integration is integration by parts. It is not something else. It's just a different way to organize it. And the way that we organize it is by putting our u's and our v's into a little table. And I'm going to show you how that works. Alright, so our original problem was x cubed e to the x dx. So when you use tabular integration, you make a little t-chart, and we're going to organize our u's on the left-hand column and our dv's on the right-hand column. So whatever you choose u to be, we write it over here on the left-hand side. Whatever we choose dv to be, we put it over here on the right-hand side. And we don't really bother with the dx part of it. So the way this works is we are going to keep taking the derivative of u until we get 0. Okay, so the derivative of x cubed will be 3x squared, then 6x, then 6, and then 0. So take the derivative until you get a 0. On the right-hand side, we will integrate as many times as we took derivatives. So I have 4 of these written down. I'm going to take the integral of it 4 times. And this one's a nice easy one. It's just e to the x, so it stays at e to the x. Okay, now the way that this works is that these are paired diagonally. And the reason why they're paired diagonally is because over here, you know, when we did the integration by parts, we actually went this way, right? Our uv, and then our v du, and then our uv, and our v du. But if you'll notice, everything here repeats. This line right here became this line over here. This line right here became this same line down here. So they kind of repeat over here. That's why it goes sort of diagonally all the way down. And there is a little catch here. When we multiply these, whatever the product is, we're going to keep it positive. Whenever we multiply these two, we're going to keep that product negative, positive, and negative. Okay, so let's take a look at what we have. Doing the first diagonal going down, we'll multiply. So that's x cubed e to the x. It'll be positive. Then we do these two, and we have a negative 3x squared e to the x. Then the next pair will be plus 6x e to the x. Then the next one, negative 6 e to the x. And you have to remember the plus c, because no one's going to tell you to put that in there, but you are done integrating. So this right here, same answer as what we did above. So let's do a couple more examples. This one's going to be e to the x sine x dx. Now this one, if you'll notice, is a little bit different than the previous ones because I do not have a polynomial function in here. So which should we let equal to our u and which should we let equal to our dv? Okay, some of you guys might be thinking, let's let u equal to e to the x, and some of you guys might be thinking, wait, we could let u equal to sine x. Actually, it doesn't matter. It'll work both ways, but I'm only going to work out one of them right here. I'm going to work it out with u equal to e to the x and dv equals sine of x dx. So I'm going to have du equals to e to the x dx and v1 equal to negative cosine x. So we have to be a little bit careful here when we take the integral and remember that the derivative of a negative cosine will give us the positive sign. So working this out, let me write out my original problem here. This is going to equal to uv, so notice the negative, minus v du. And it's minus a negative, so this is going to become a positive, e to the x cosine x dx. Now I kind of have a problem. I still can't integrate this. I had an e to the x sine x, now I have an e to the x cosine x. Okay, so I'm going to do integration by parts one more time. But I'm going to let u this time be e to the x, and my dv will be our cosine x. Do not switch them and make it cosine for the u and e to the x for the dv, because if you do, you're going to go back in a loop and you're going to end up with the same problem you started out with, and it's going to come out 0 equals to 0, and you're going to wonder what happened. Okay, you will just have undone what you did with your first integration by parts. So make sure you keep it consistent. If u is going to be e to the x, your next u will also be e to the x. So when we integrate here, we're going to get v2 equals to sine x. So now let's write out what we have. I had originally a negative e to the x cosine x. So now I'm going to do my uv, so e to the x sine x, minus v du. So minus e to the x sine x dx. Now, what has happened? We just got back the same integral that we started out with. This is actually going to be a never-ending loop, and this is a unique kind of problem. This goes back and forth because e to the x never really ends when you take the derivative or the integral, and same with the sine function. It goes back and forth from sine to cosine, sine to cosine. So there's a trick here. The only way we're going to be able to do this is to take this integral. If you notice, it's the same one that we had at the beginning. We're going to add it over to the other side. So we're going to have two of these integrals that we're trying to solve for. And once I move it over, because I have gotten rid of the integral, I'm going to have to write in my plus c for a constant, because these actually had constants with them. And can you guess what we have to do to solve for our integral? I only want to solve for one of these integrals, integral of e to the x sine x dx. I don't want two of them. We're going to have to take the 2 and divide everything by it. Everything including the c. Now I'm going to rearrange these also, so I'm going to have e to the x sine x minus e to the x cosine x. I'm going to put a 1/2 out here in the front, and I'm going to change my constant to a c naught because I actually divided it by 2. And this is our answer.